Hello everyone, welcome to the class ECE317, the digital signal processing. Today we will keep working on the linear phase systems. Okay, ECE317. This will be the 13-week Wednesdays class. Okay. We consider linear phase systems. Linear phase systems. So the feature is just like this. H of e to the j omega. This is frequency response. We check the angle. This angle will equal to some negative with a constant r times omega. So a linear phase system, that means a system with the angle of the frequency response equal to this kind of things, where the omega, we suppose the omega is a value from negative pi, omega, negative pi to pi, negative pi to pi, and alpha is a constant. This alpha actually it will appear as a delay of the signal. If we have a system like this, right? We have this system h of z. I put this h of z. Input x of n. If x of n is a kind of sinusoid, for example, if it is a cosine of omega 0 n, then this side, what is the output? If we have these, then output will be the magnitude times cosine of omega 0 n plus the angle. But now the angle is alpha omega. Alpha omega 0. Right? Here's omega 0. This is omega 0, then this should be omega 0. Like this. So we can write it as e to the j omega 0 times cosine of omega 0 times n minus alpha. So this is kind of a shift on n by alpha. N is a time, right? Shift on n. So we have a time shift. It's a time delay. It's a kind of time delay. But not exactly. Only when the alpha, they are integers. Only when r is an integer. This is really a delay in discrete time case. If r is not an integer, if alpha is not an integer, it's also kind of delay, but not exactly delay. Last time I gave an example to show that. Okay, now we consider a special case. Now consider like this. Consider a system h of z with a feature. First one we want it is a linear phase. Okay, linear phase, right? We're studying linear phase system. But secondly, we want more. We want this is a FIR field, and the third one we want it is a causal one. We want these three. We want three. It's linear, it's FIR, it's causal. Then what will be this field? We want to find the feature of this field. Okay, now h of z equal to magnitude of h, writing the frequency response. H of e to the j omega equal to h magnitude of h of e to the j omega times e to the j, then angle of h of e to the j omega. Right? We have this one. Now we consider these. We consider this part as something else. I say this is a HR e to the j omega equal to the magnitude of h of e to the j omega. I suppose HR is another system. It is just this part, and we know it is a linear phase, right? Because it is a linear phase. Oh, sorry, this pen is I need some more pen. Okay, because of the linear phase, that means the angle of H will be negative alpha omega, right? When omega is smaller than pi, or smaller than equal, right? In this case. So we have H of e to the j omega equal to HR e to the j omega times e to the negative j alpha omega. Now we have this one. So what is this? Actually, we can check the table of the Fourier transform. Oh, I should open it. Have the table. Is it here? You see? Make it hard. Okay. Is it here? You got it? Here. The second row. Here in the fractions domain is e to the negative j some omega nd. Right, omega nd. This nd is similar with our alpha here. You can compare. Right? We have e to the negative j d omega. Right? And in the table, large. Okay. Here's e to the just here I can see it is a HR times HR of e to the j omega. This one is you can see this is just this capital H. Then times e to the negative j. This is omega and nd. This is a negative j omega and alpha here, right? It's alpha. So this alpha is as same as this nd. So this one was related with, in the time domain there will be x of m minus nd. Now we are not x, we have hr. So we can have this. We perform the dt ft with the inverse. That will be hr of n minus alpha, right? Where it will be this one. It will be this one. You got it? Where hr of n is the dt ft with the inverse of hr. You got it? Yeah. So we find this from the table, right? But of course, we need a requirement if alpha is an integer. All right. So we have this one. It is shift. So go back to time domain. It will be shift of hr. And we know this one, if we perform the dt ft with we directly apply dt ft here, what we will have? We will have the impulse response, right? So that means our impulse response is hr with a shift by alpha. So we have this. So that means hn is a shift of hr of n. Actually, this is a hr of n minus alpha. We have a shift. And okay, then what is hr? hr is coming from this capital hr. Capital hr is this one, magnitude. So this one we have two features. It is real and positive. right? You take the absolute value, you take the magnitude of this complex number, you will have a real number, a positive real number, positive real number. Okay, so HR is a positive real number. Then what can we say about this HR? I say that because HR of e to the j omega is real and positive. Actually, we only need the real here. So yeah, we check the table. We have another result for Fourier transform. Is here. Let me make it large. Real, okay. Any real x of n. You can see, for any real of x n, we have not real x n. We need a real in frequency domain is real. In frequency domain is real. Which term we can see that? Okay, it's here. It's here. Capital XR, that means the real part of the of capital X. Now we only have capital XR. We do not have the XI. Right? Here we separate X with XR and XI. We only have XR. We only have XR. That is HR. Our HR. This is HR. Then we go to the time domain. It will be an even. Right? It is even part of X. Now we only have this even part. That means the signal in time domain, it is just even function, even signal. Okay, so I will claim our not this is here. I will say HR of n. HR of n is even on n. Now n things like if this is n, the HR will be something looks like this. Right? If here is negative, here will be negative. If here is like this, here will be like this. Even. Yeah, even. The both side, these two sides, they were symmetrically same value. Right? They are same like this. Should be even. Something like this. Something like this. Okay. So then we say the h, what will be h of n? Hn is hr of n minus alpha, where it looks like this. Here's alpha, then symmetrically according to this alpha. Something like this, right? Even here, even regard this is n equal to alpha. N equal to alpha. Now here I say even. This is not really even. People usually say even. There we use the original point at the center of the symmetric, right? But now we shift it, so this point will go to here. Go to here, so your even looks like this. Even looks like this, you know. Yeah. And also we know h, and furthermore, h of z, we know it is a causal. That means Hn will equal to 0 for n smaller than 0, right? For negative n is 0. So here this should be 0. We do not have element. We do not have non-zero values, right? So we have this. Okay, so then we say h of n will be what? Will be something. You have some value here, then 0 after n go to negative. And symmetrically, this side will be same thing. Right, same thing. So we will have h of the center at alpha, right? H of n will equal to 0 if n smaller than 0. And h of 0 will equal to, okay, h0 is here, right? Equal to some point here, symmetrically, right? These two values will be same. These two values will be same. And here's r, here's r. Here will be what? Here will be 2 alpha, right? 2 alpha, or maybe 2 alpha plus 1. We have several cases, right? You can see we have 2 cases. For example, I have 1's here, 1's here, 1's here, 1's here. This is n equal to 0, 1, 2, 3. So symmetrical, right? They are same. They are same. So this point will be now this is alpha. This is 2 alpha. Right? This is 2 alpha. And another case is like you have these, 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 like this one. This is a 0, 1, 2, 3, 4. Yeah. Oh, it's always 2. Yeah, here's alpha. Here's alpha equal to 1.5, symmetrical according to 1.5. This is the case alpha equal to 2. So in both cases, this point will be 2 alpha, n equal to 2 alpha. So this is h of 2 alpha. 2 alpha. The h of 1 will equal to h of 2 alpha minus 1. Right? Yes, this point and this point, or this point and this point, and so on. Like this. Until alpha, okay, until the integer is just smaller than alpha. Maybe equal to alpha. Here alpha is 2. Or smaller, it's still smaller. Smaller than these two will be same. And this one doesn't matter. You only have one value here, right? And here, this point we do not have value because it's n must be integer. N must be integer. So we can have h can be described by this way. Okay, this is the feature. This is the feature for the linear phase, causal, and FIR. Okay. And okay, FIR. I also need this side. This should be 0, right? Symmetrically. Here's a 0. Here's also 0. So h of n equal to 0 if n larger than 2 alpha. Larger than 2 alpha. And what is r? R is the delay, or we say angle of h e to the j omega will equal to negative r omega. We have this. Okay, so we have this one, we have this one. So these two features give us, very convenient. You just look at the h of n, the impulse response, then you can know, okay, whether this is a linear phase, what is the time delay, what is the angle. Okay. Now let me study example. You say h of n, suppose h of n, this one, it is 1 for 1, okay, just 1 for 1, like this. Here's a n equal to 0. Okay, then we will say, I can say h of e to the j omega is linear phase, and its angle will equal to negative. Okay, so this is the center, right? Center here. Center n equal to 1. N equal to 1. So this is just 1 times omega. Alpha equal to 1. Alpha equal to 1. Okay. And another one, h of n equal to like 1 to 5 to 1. Okay, this is a n equal to 0. Say this is A, this is B, example B. Then this one, this is also is linear phase, and the angle of h of e to the j omega will be what? You know, this is the center, right? Center here, the bar. Center n equal to, now is n equals 0, 1, 2, n equal to 2. That means alpha equal to 2. Alpha equal to 2. So this one will be negative 2 omega. Now we know the angle. We know the angle. In other words, 2 is the delay. So if you send the sinusoid as an input, then output will be a sinusoid with same frequency and with 2 as a delay, as a time delay. No matter what is the frequency of the input, right? Input side you can use different frequency. In generally, for different frequency, the delay is different. The output side, some frequency they delay more, some frequency signal they delay less. But for linear phase system, the delay are same, no matter what is omega. It's always delayed by 2, like this in this example. Okay. Alright. It seems good, but we still have problem. What is the problem? We say this is linear phase. Are you sure? I just use the previous result here. If it is a linear phase, we have this. But if we have this, can you say it must be a linear phase? Well, the thing is not always. I said like this, but I still have problem here. I still have problem. I need to check. Let us see. For A, what is h of e to the j omega? It will be Fourier transform of this signal, right? So we just, by the definition, it is 1 plus 4 times e to the negative j omega plus 1 times e to the negative j 2 omega. Right? Okay, now we remove this outside, and then I have e to the j omega left, plus 4 plus e to the negative j omega, and times e to negative j omega. Okay, you see, this part, this is a j times negative omega. So the angle, it is just this part, right? Negative omega. This is the angle. But this part, is this the magnitude? Can we say this part is the magnitude? Okay, we need 2 conditions for this. Real, positive. You need to check these 2. If both answer yes, then this is yes. This one will be the magnitude. If it is not real, or if it is not positive, even it is real but not positive, you cannot say this is the magnitude. Magnitude must be real and positive. Right? Okay, we will check this part. And this part, then we need to use this. We need to use we know e to the j omega equal to cosine omega plus j sine omega. Right? This is a Euler formula. Euler formula. And also we have e to the negative j omega equal to cosine omega minus j sine omega. So we do summation. We have e to the j omega plus e to the negative j omega equal to 2 of cosine omega. So we have this part, e to the j omega plus 4 plus e to the negative j omega, which is this 2 summation is 2 of omega, 2 of cosine omega, and plus 4. Is this real? Real? Okay, no problem. Right? This is real. And is it positive? Yeah, we know this is positive, right? This one cosine omega is value between negative 1 and 1 when we equal. Then 2 cosine omega will be value between positive and negative 2. Right? So this one must be positive. Right? Okay, so we know this part, it is real and positive. Then we have the right way. H can be written as multiplication of two parts. The first part, it is real and positive, and the second part is exponential power, with the power is negative. Power is j times a constant times negative constant times omega. That constant now is 1, negative 1 times omega, right? And that is the angle. That is just the angle. Okay, so now we can claim our result. H of e to the j omega magnitude equal to this part is a 2 cosine of omega plus 4. Put it like this. And the angle of h of e to the j omega were equal to just this part, right? Is negative omega, negative omega, negative omega. And we know the time delay r equal to 1. Right? This is a linear phase. Linear phase. Now, of course, all of these we have a requirement. We are discussing this. All of these we suppose omega is from negative pi to pi. Negative pi to pi. Okay, so it is a linear phase, no problem. And the second example, I have two here, right? I have two here. This one. For B, h of e to the j omega were equal to, now what is h? H is here. H is 1, 2, 5 to 1. 1, 2, 5 to 1. So by Fourier transform, it will be 1, this is 1, then plus 2 times e to the negative j omega, and this is 5, I need 5 times e to the negative j 2 omega, and then 2 again, e to the negative j is 3 omega, and 1 times e to the negative j just 4 omega. Right. 1 omega, 2 omega, 3, and 4 omegas. Actually, first term is also have exponential power, but the exponential power, it is e to a 0 omega. So that's I don't need, yeah, e to the 0 is 0, is 1, right? So here just 1. Okay, then how to do it? Okay, we say we know, actually we can guess the center will be here, right? I said this one, this is the center is 2 and alpha should be 2, so it will contain the part with that one, right? Let me see. With the thing looks like this. Oh, sorry, wait here. Yeah, we need to write in this way, right? Something times e to the negative j alpha omega. This should be alpha. Now alpha is 2. Now alpha is 2. Alpha is 2. So we have e to the negative j 2 alpha. So we have e to the negative j 2 alpha. We hope we can find something looks like this. And what it is? This is just this one, right? This is the middle one. Middle one, I have this term. I move it outside. I put the rest of the summations inside this. Inside, put them together. So I move this one. I move this out. So I need e to the positive j2 omega, right? You times these two together, you have 1. And then second term, it is plus 2 times e. I need to move 2 of it, and I already have 1, so I need 1 more. So I have j omega. In other words, you times these 2, you get this one. And then I need times, this is 5. I already have 5. And this one, I remove 2, I have 1 left. Plus 2 of e to the negative j omega. Oh, I need 1 more space. And I write here, alright. Sorry, plus e to the negative j 2. I move 2 outside. I have 4. So here I have 4. So move 2. I have 2 left. I have this one. Okay, then we have same thing. We can try to write these in sine and cosine. So we can use that formula. We can use that formula again. With that formula for the sine, for the exponential power, and the sine and the cosine. We have these two. We try to use things similar like this. And actually, we can write. We have this one. You see, we have this one. For this one, we can have more generally. We have this one. We can have e to the ja plus e to the negative ja. This one, it will be 2 of cosine of a. We always have this. We always have this. So we have h of e to the j omega equal to, okay, you see, here's e to the j some a is 2 omega. Here's also e to the j a with a negative a, right? Negative a. So here should be 2 of cosine of a is 2 omega. Right. These two terms you put together, you get this one. And then this one and this one. This is also e to the j omega, e to the negative j omega, so e to some ja, e to some negative ja. Then this will be 2 of, okay, I already have a 2, so here should be 4. 4 cosine of, here should be a is omega. Alright, and 5 is already a real number. And here I just called it negative j 2 omega. Alright, now you see this part is what? This is already a real part, real one. And we also need to check whether it is a positive. Now we'll check whether it's positive. It is a positive, then we're done. We know this is a magnitude, and this is part related with the phase. Alright, is it positive? I have 2 cosines. If you check this one, this is between 0 and 1. So the whole thing is between negative and positive 2. This is between negative and positive 4. So the summation, there will be between 0, negative, okay, right here, cosine 2 omega times 2, there will be between negative 2 and positive 2. And 4 cosine omega, there will be between 4 and negative 4. So you do summation, you are saying this is negative 6, this is positive 6, the summation, right? Then you plus 5. Can you make sure this is positive? You're not so sure, right? Then we can check one more. We do more calculate. We can use computer to do more calculations to see how about this function, whether it is always positive. Right? I try the omega. You can see it. Okay. Let omega is run from. Actually, we only need omega run from 0 to pi, right? 0 to pi with step 0.01 to pi. We only need this part, and then that is HR, right? That is HR. I use this same notation. HR is 2 times cosine of 2 times omega, and plus 4 times cosine of omega, and plus 5. Alright, this is HR. Then let's plot it. You can see W and HR. How it looks like. Oh, it looks like this. Like this. This is when omega run from 0 to pi. Then the curve looks like this. It is always positive or maybe 0. Positive or maybe 0. So this is also good. You can have just 1 point at 0. Alright. but maybe it's negative. We can see the minimal of HR is what? It's 2 dot. Oh, this is 2. Oh, here's 2. Okay, it is always positive. Yeah, we can see more. This is a W equal to pi. If I give the 10 pi, 10 pi, that means we have 5 cycles, right? Every 2 pi is 1 cycle. 10 pi is 5 cycles. I don't need too much. And use 3 cycles will be fine. Then we can see how it looks like, right? 6, that is 3 cycles. And HR is also the same function, but omega now is omega has long intervals. And then plot this one. Oh, it looks like this. Look like this. Alright. The minimal value is 2. So this one actually is value between 2 and 11. 2 and 11. Yeah. But the thing is here we need to use some tools to calculate this. Here I say by my lab. This HR is larger than or maybe equal to 2, so it's positive. And this is HR, right? This is HR. This part is HR. It's positive and real. Positive and real. So we can say H is a linear phase system with angle will be the it is look like this, right? I have 1, 2, 5, 2, 1, right? So the center is here. This is n equal to 0. This is n equal to 2. So center is 2. This is a negative 2 times omega. Right? So alpha equal to 2. Here should be negative alpha omega. And of course, this is just for omega between negative pi to pi. If you go outside, it is not still like this. We can see more. Yeah. You can see here, this is I have an omega, right? I have an omega. Now let me give H. H will be what? H will be HR times exponential power of negative J times alpha. Alpha now is 2. 2 times omega. Right? This is a H. This should be H. This is a complex number. It should be H. Oh, the dot. I need here. I need to put the dot here. Yeah. So because both are vectors, so I want them multiplied together. When they times together, I want them times element by element. So I need that dot before the multiplication. Okay. So by this H, I have H. Then I just plot H, the angle of H, right? Angle of H. How it looks like. You see, it is a segment, right? Separate segment, line and the line and the line, and not always a whole straight line. In one cycle, from 0 to pi, actually from negative pi to positive pi, it is straight line. Then from pi, here's according to pi, omega is pi. Here's omega is 3 pi. From pi to 3 pi, not 3 pi, here's what? Here's 1 dot something. Oh, it's half pi. Half pi Oh no, it is coming out here. This is you see this value. Here the angle is positive pi. Here the angle is negative pi. Actually, they can combine together. Whatever, yeah. Things like that. Things like that. But what's wrong here? I think I need one cycle, right? One cycle. If I give omega is I change different omega. If omega is now it's 6 pi, I go to negative side. Negative pi to positive pi. From negative pi to positive pi, I give one cycle. Let's see what happened here. This is one cycle. Then HR equal to this, and H equal to this, and plot W and HR. Oh, this is not straight line. I want a straight line. Why is it not? Oh, it's separate. Actually, you see this angle. This is according to the angle should be pi, right? 3 dot something should be pi. This is negative pi. So these 2 points, actually they are same angle. But in MATLAB, maybe they have some restriction. They want to represent the angle just between positive and negative pi. So this point is going up. But actually this point should be here. Right? Should be same point. So you can see this line, if you just look at the graph, they are separate. But you consider they represent the angles. This line, this straight line, and this straight line, they are same line. They are connected. You got it? Yeah. So this should be one straight line. So this is linear phase. All right. Yeah. Okay. So this is another example. Now let's consider one more example. It is not really linear. Linear phase. Okay, one more example. I use h of n now as it's 1 1 1. Yeah, just 1 1 1. Here's n equal to 0. Okay. Then we can see what we know. This is also symmetrically, right? This is n equal to 0, n equal to 1, n equal to 2. So here's the center. Alpha should be 1. Right? Things looks like this. But h of e to the j omega is what? Is 1 plus e to the negative j omega plus e to the negative 2 j omega. Then I want to write it as a real part times e to the negative j omega. Right? I have the center one in this one. I moved it here. Then this one I have e to the positive j omega left, and here's 1. Here's e to the negative j omega. So these two I combine. I have 2 of cosine omega and plus 1, and e to negative j omega. Okay, this one it is real, no problem, but not positive. Right? It's not positive. If this value should be between positive and negative 2. When this one is negative 2, the plus 1 you get a negative 1. So this is not always positive. Not always. Sometimes it is positive, but some other time it is not positive. So this case it is not linear phase. So H Z is not a linear phase system. But we have a name for it. We call it the general linear phase. General linear phase system. Yes, a general linear phase. not the exactly linear phase, but generalized. After you generalize the concept, you know, this, we call this a general linear phase system. And that alpha is called group delay. In linear phase case, this alpha we just call it as a delay. Now we call it as a group delay. Because this is not linear phase, so for different frequency, the delay might be different. But we still have this alpha. This alpha, if you check the graph of the phase, that will be the slope. Now we still call it, that will be slope of the graph. Okay, just use my lab to see. Okay, so here we have that h will be 1 plus exponential power of negative j times omega, and plus exponential power of negative 2 times j times omega. Right? We have this one. This is h. This is new h. Now we plot omega regarding the angle of h. Let's see how it looks like. It looks like this. Look like this. It still looks like a straight line, but now these two lines, they are straight line, but you cannot connect them together. This point is 1 dot something. Here's 1 dot something, and this point is 2 dot something. So the difference between these 2 points is not 2 pi. If the difference between them they are 2 pi, then as an angle they are same, right? As our previous example. Then these 2 lines you can think they are same line, they are connected. But now the difference is not 2 pi, it's a pi, right? This is 1 dot something, this is 2 dot something. Totally difference is a negative 2 to 1 is 3 dot something. Should be pi. The difference is pi. It is not 2 pi. Not 2 pi. So these two are different. You can think they are broken. They are not same line. However, they have the same slope. You see? This line and this line, they have same slope. And that slope will be this alpha, right? The alpha is related with a negative, right? We know that for linear phase, the alpha, yeah, the angle will be some negative alpha omega, right? The alpha, negative alpha is the slope. Negative alpha is the slope, and alpha is the delay. Now is in this part, in the middle, this longer line, the slope is also the delay, right? The slope is also the delay. It is just alpha, negative alpha times omega. But this part is not. Let me give the graph. The graph looks like this. This is omega. It will be a straight line. Look like this, like this one, not like this one. And this is this part is this is angle of h, right? Here angle h is equal to negative alpha. Alpha is 2. Alpha is 1. Alpha is 1. I just put alpha. Alpha equal to 1. Negative alpha omega. And this place is equal to negative alpha omega plus a pi. Right? Here's a plus a pi. Negative alpha plus a pi plus pi. If it is plus 2 pi, you can think they are same thing as angle. But now plus pi, they are not same. So this one, now alpha is not a delay. But we call this group delay. Now we have different name for it. We call it group delay. This is still a straight line. This is also a straight line, right? Different line. And the slope, this is also slope. But this is not really the delay. We call it group delay. Group delay. Alright. Okay. That's all for today. See you next time. Bye bye.